Now, I have a very specific rubric that I have to follow for grading this lab, and it requires a lot of minuscule pointage, as you can see. 0.4 for the structure, 0.1 for each one of these answers, 0.1 for the number of valence electrons. So question number 3 in part 4 is worth 1 point, but it's divided up. Of course, if you don't get the structure right, you'll probably get some of these wrong as well. I'm not going to match what's in the right hand to the left hand. I'm just going to mark it correct or incorrect according to what the chemical actually is. If you get this wrong and then you say, oh, it's a trigonal planar, and you write whatever you draw turns out to be trigonal planar, so you write trigonal planar here. I'm not going to check that. It's just going to be right or wrong based on the actual molecule. So otherwise, of course, I would end up doing about 500 of these problems as I check and make sure this coincides with this. So I won't be doing that. That will take too much time, and I already know how to do these structures. So you are the ones that have to make sure this is right so that this can be right. Now, the purpose of this lab is to give you a lot of practice on Lewis structures, so you will learn it and you'll be able to do it correctly in the future and on tests and problems. It's a learning experience, correct? But I'm not in the lab to help you step by step. I would love for you guys to come to office hours and check your work with me. But if you are unable to do that, there are several online helps that you can use to check and make sure you got the right structure. It is okay to do the structure and then check it, because this whole lab is about learning how to do these right. If you do it wrong, you hand it in, you get it back 2 weeks later, you maybe look at what you did and what you got wrong. So I'm not recommending that as a learning strategy. What I'm recommending is you do your best, do 2 or 3, then check them with one of these online tools and see where if you got it right or what you got wrong. And that way this becomes a learning experience and not something you rush at the end of Saturday or Sunday night. The tool I like best is PhET, because as you can see, you can build the molecule and it shows you in a space-filling way what it will look like. You can do single, multiple, and even just fool around and make up molecules and see what they would come out looking like. So you could see this one here. If this is the central molecule, that would be trigonal planar, because it's the central molecule. If they said, oh, what's the structure around that carbon? Well, that carbon's different. That carbon would have a tetrahedral structure, wouldn't it? So this is a great one, and PhET has 2 different ones. This one is called molecule shapes, where you put in the number of bonds, the number of lone pairs, and you'll see what the molecule will end up looking at, again in a 3-dimensional way. And then Wolfram also, you can check your Lewis structure. As far as I've seen, it doesn't give the 3D, but it gives the correct Lewis structure in a flat way. And let me remind you, as you're trying to figure out these molecular geometries, there are tables in the lab and in your textbook. So, to reiterate, remember to write the number of electrons even in part 4. Always write the number of electrons to get full credit. Second, in part 4, make sure you do the 3D structure, not the flat structure. Unless it's planar, there should be some wedges, or linear, there should be some wedges and dotted bonds in there. Third, check your work as you go using those online tools. Now, let's move on to the harder types of molecules. There are molecules which are exceptions to the octet rule. Some of the molecules will have an odd number of electrons, or ions, and that will result in a free radical. The odd electron goes to the least electronegative atom. Boron, being very small, tends to form compounds with only 6 electrons around boron. In other words, it's happy with 6 electrons. 3 expanded octets can form from period 3 elements and beyond. For example, phosphorus can be happy with 10 electrons around it. And sulfur, phosphorus, xenon, chlorine, and iodine will take even 6 electron groups or 12 electrons around them as the central atom. These are some examples drawn in 2D, not in 3D, of what some of these exceptional molecules which have expanded octets around the central atom look like. So they have more than 8, they have 10 or 12 electrons, 5 or 6 electron groups around the central atom. This molecule here, phosphorus, has 4 electron groups, but 10 electrons around it. So it doesn't have an expanded octet, it has 10 electrons. It doesn't have an octet, it has 10 electrons around it. This xenon molecule has 12 electrons around it in 6 electron groups. And this phosphorus in this case has 5 electron groups and 10 electrons. Now let's talk about polarity of the molecule. Here is that familiar electronegativity chart, which tells us that fluorine is super electronegative, oxygen and nitrogen are pretty electronegative, hydrogen and all these others are not too much, and you can get the comparative values. And here are 2 molecules, both made of 2 atoms. In the case of chlorine, it's 2 chlorines, so they both have, of course, the same electronegativity number, and of course they're both going to be pulling on the electrons with the same desire, and so there will be a nonpolar molecule. Whereas in HF, fluorine is much more electronegative. It will be pulling on the shared electrons much more than hydrogen, and so there'll be more electron density here on the right, which means there'll be more negative charge on the right overall, and that means it will be a polar molecule. Here are a couple more molecules. Carbon dioxide is, even though it has 2 different kinds of atoms, carbons and oxygens, because they are in space exactly symmetrical, the 2 bond dipoles in the 2 bonds balance each other out, so the whole molecule has no dipole moment. Whereas in water, remember, oxygen even has some electron groups up here, some non-bonding groups. And so there's a lot of electronegativity, a lot of electrons, a lot of electronegativity here, and oxygen is much more electronegative than hydrogen, so that each bond has a bond dipole, and it's not symmetrical. These arrows are not exactly balancing each other out. I like especially the idea of a rope, right? If you put a rope, if you're the central person and someone's pulling you on a rope with your right hand and someone's pulling equally on your left hand, you're not going to go anywhere. But if you are oxygen here and someone's pulling down and to the right with one rope in your right hand and down and to the left with another rope in your left hand, and they're pulling with equal force, they're not going to balance each other out. You're going to move down, right? So the same thing. So these do not balance, whereas these do balance each other out. No dipole moment, dipole moment. So a molecule is polar if it satisfies 2 conditions. It contains polar bonds. We can draw one of these arrows pointing to the more electronegative atom between 2 atoms in a bond, and the polar bonds do not cancel each other. Like here in CCl4, they are all pulling with equal force and they are exactly canceling each other. Here, of course, they are not. And here, even though it's a tetrahedron, this fluorine up here is pulling much harder on the electrons from carbon than these guys, so they do not balance each other out. Basically, in practical terms, if the molecule is perfectly symmetrical, 360 degrees in 3D, then, or in a plane, then there's no dipole moment and the molecule is nonpolar. If there's anything odd and asymmetrical about it, like replacing one of the chlorines with or one of the hydrogens with a chlorine, then it will be a polar molecule. It will have a dipole moment. Well, I hope this has been helpful. Remember the details I mentioned. Part 4, I must have the number of valence electrons in the molecule and also draw 3D structures in part 4. Very helpful to talk through some of this stuff with somebody else. I look forward to seeing you either in Zoom or office hours or hearing from you by email.